What if the first aliens live in the dark? What if the first alien life we find isn't on a planet at all, but in a pitch-black ocean under the ice of a distant moon? A world with no sunrise, no blue sky, and no starlight reaching the place where life actually lives. In the hunt for alien life, we usually picture something very specific. A small, Earth-like planet, gently warmed by its star. Liquid water on the surface, clouds, continents, maybe even an atmosphere we could read like a book. That mental image is powerful because it is, of course, our own. Life arose here, so we instinctively treat worlds that resemble Earth as the most promising, the most habitable. But what if that intuition is wrong, or at least incomplete? What if the most common homes for life in the universe are not sunlit planets in a Goldilocks zone, but hidden oceans sealed beneath ice, orbiting giant planets instead of stars? Entire ecosystems thriving with no direct starlight at all, no days or nights, only the slow flexing of rock and ice, the churn of chemistry, and the faint glow of internal heat. We already know this is not just science fiction. On Earth's own seafloor, far from the sun, life flourishes around hydrothermal vents. There, bacteria harvest chemical energy instead of sunlight, and whole communities of strange animals build their existence on that invisible power source. This means that light from a star is not the only way to run a biosphere. If that works here, deep under our oceans, why not under the frozen shells of distant moons? It should be noted that some of the best candidates for such dark oceans are already in our solar system. Europa, with an ocean that may hold more water than all of Earth's combined. Enceladus, spraying its hidden sea into space through icy geysers. Titan, with alien lakes on the surface, and, beneath, a buried water ocean. Even larger moons like Ganymede and Callisto may hide stacked layers of liquid water. And beyond our own system, there could be exomoons we cannot yet see directly, quietly orbiting giant planets in distant habitable zones. So it's time to find out the truth. If moons can host deep, stable oceans powered by tidal heating and chemistry, then many of the most promising places for life might be these small, overlooked worlds. Optimistically speaking, there could be far more habitable real estate in the universe than we ever imagined, simply hiding in the shadows of gas giants. So, let's begin. In this video, we'll move systematically from Europa's hidden ocean to Enceladus's plumes, from Titan's lakes to hypothetical exomoons, and ask a bigger question. If life can emerge and persist in these extreme environments, what does habitable world really mean anymore? Why moons might beat planets at hosting life for decades? We thought we knew where to look. In the hunt for alien life, the obvious targets were Earth-like planets, sitting neatly in the Goldilocks zone of their star, with liquid water on the surface and an atmosphere a bit like ours. That picture is simple, comforting, and now very incomplete. Because while we were busy cataloging planets, the icy moons in our own solar system started to revolt against that neat story. Europa, Enceladus, Titan, Ganymede, even distant Callisto, these are not just frozen rocks tagging along in orbit. They are complex worlds with oceans, chemistry, and energy. It should be noted that some of them may contain more liquid water than Earth itself. If water is the key ingredient for a habitable environment, then suddenly, moons might outnumber planets as potential homes for life. Why is that such a radical shift? Planets are hostage to distance. To keep surface water liquid, a planet has to sit at just the right separation from its star, not too hot, not too cold. Move Earth a little closer to the sun, and our oceans boil. Move it farther away and they freeze. But while planets are chained to the Goldilocks zone, moons can cheat. This means a moon orbiting far beyond the traditional habitable zone can still maintain a deep global ocean. The trick is internal heating. As a moon orbits a giant planet, its interior is flexed by gravity, like a stress ball being squeezed again and again. That tidal flexing generates heat. Add in radioactive decay of elements in the rock, and possibly hydrothermal vents on the seafloor, and you can keep an ocean liquid in places where sunlight is barely a faint glow. Optimistically speaking, whole ecosystems could exist there, without caring whether the star is bright, dim, or even nearby at all. If that is true, the stakes are enormous. Habitable conditions would not just cling to a narrow ring around each star, they could be scattered throughout planetary systems, wrapped around gas giants, deep in the cold outer regions. In a universe with hundreds of billions of stars, each with the potential for multiple moons, the number of possible habitats explodes. So it's time to find out the truth. Are we vastly underestimating how common life-friendly environments really are? However, there is a catch. These oceans are hidden. We cannot see glittering blue surfaces, we see blank, white ice, tens of kilometers thick. To detect a subsurface ocean, we have to read subtle clues, tiny wobbles in gravity, magnetic fields shifting as salty water conducts electricity, or plumes of vapor and ice erupting into space, like we saw at Enceladus. The data are indirect, the interpretation's difficult, and every conclusion comes with large uncertainties. So where do we start testing these ideas? We start at home. Our own solar system is the only place where we can send spacecraft to orbit, to fly through plumes, to feel gravity fields directly. Europa Clipper, JUICE, and Dragonfly will turn these distant dots of light into detailed worlds. And as we tour the most promising moons one by one, we have to ask a final, unsettling question. What happens if one of them already shows signs of life? From Earth 2.0 to ocean worlds, a quiet revolution. If that question makes you slightly uneasy, it should. Because in the hunt for alien life, something subtle but profound has happened over the last few decades. For a long time, our strategy was simple. We wanted Earth 2.0. Astronomers pointed their telescopes at distant stars and searched for rocky, Earth-like planets orbiting in the so-called Goldilocks zone, where liquid water could exist on the surface. Find a twin of our world, the thinking went, and you maximize your chances of finding familiar biology. But while that idea is intuitive, the data have been quietly rebellious. Many of the most intriguing worlds we have found are not neat Earth clones at all. They are low-density, water-rich planets, super-Earths, and mini-Neptunes that may be wrapped in deep global oceans or thick ice layers, with no solid ground like the continents we know. Instead of blue marbles, we keep seeing strange, drowned cousins. This shift forced astronomers to ask a harder question. Do we really need a sunlit ocean on the surface of a planet, or do we just need liquid water somewhere, protected and stable, for long periods of time? This means the spotlight widened from classic habitable zones around a star to something more radical, ocean worlds. So, what are ocean worlds exactly? In clear terms, they are bodies that hide substantial liquid water beneath their surfaces, usually under ice. They can be planets, but in our own solar system, the best examples are moons. Europa likely holds more than twice the water of all Earth's oceans combined. Tiny Enceladus, with its dramatic plumes, may have a global sea and contact with a rocky seafloor. Titan seems to stack the deck, with methane lakes on the surface and a buried water ammonia ocean below. It should be noted that several of these moons are smaller than our own moon, yet they may out-ocean Earth. Here's the pattern interrupt. Sunlight is no longer the only game in town. Tidal heating, as these moons flex in their orbits around giant planets, can keep interiors warm for billions of years. Hydrothermal vents on their seafloors could provide energy and chemistry very similar to the environments where life may have started here. Space agencies have noticed. Europa Clipper and ESA's JUICE are not generic planetary tours, they are precision instruments built to test habitability. They will map ice shells, sniff thin atmospheres, weigh oceans, and search for the salts and organics that betray an active interior. Dragonfly will actually fly through Titan's thick atmosphere and land, sampling its chemistry directly. Optimistically speaking, these missions are our verdict tools. Just as JWST now delivers verdicts on distant planetary systems, these spacecraft will tell us whether ocean moons truly have the ingredients for life, or whether we have been overhyping frozen worlds. So it's time to find out the truth. If we line up every moon that could plausibly hide life, from Europa and Enceladus to hypothetical exomoons around distant gas giants, which ones emerge as the most likely cradles of alien biology, and which might turn out to be the real surprises? Your map for the hidden oceans we're about to enter. So, let's begin by making this very clear. We are not just collecting pretty pictures of icy dots around giant planets. We are building a map of hidden oceans, ranked by how likely they are to host life, and by how soon we can actually test that with real data. And this is, where we follow the evidence for life in the universe wherever it leads, whether that is a familiar Earth-like planet or a moon that looks dead on the surface. In the hunt for alien life, think of this episode as a guided dive. Each stop is a different moon, a different ocean, a different experiment in how nature might build a habitable environment. But before we plunge into individual worlds, we need the rules of the game. Why can these moons host liquid water at all when they orbit so far from the sun? We will start with the basic physics, how tidal forces flex a moon's interior, how that motion turns into heat, and how that heat can keep an ocean liquid beneath ice thicker than any mountain on Earth. It should be noted that without this foundation, words like tidal heating and subsurface ocean are just labels, not tools. Once we have that framework, we will move into the heart of the Jupiter-Saturn system. First Europa, with an ocean that may hold more water than all of Earth's oceans combined, and hints of salts and possible plumes in its thin atmosphere. Then Ganymede and Callisto, layered worlds where water and rock may be stacked like a cosmic sandwich, each layer changing how habitable those oceans really are. From there, we pivot to Saturn. Enceladus will be our case study for hydrothermal vents. Cassini already flew through its plumes and tasted salts, organics, and warm water vapor. This means we have direct evidence of seafloor chemistry that could power life. We will pause here to unpack what hydrothermal vents actually are, why they matter, and how similar processes on early Earth may have helped life begin. Then we arrive at Titan, the strangest stop on our map. A moon with lakes of liquid methane on the surface, a thick atmosphere rich in organics, and strong evidence for a buried water, ammonia ocean below. Double habitability. We will explore how these two layers might interact, and why missions like Dragonfly could transform Titan from an oddball into a prime biological target. Finally, we will zoom out. How do we extend everything we have learned to exomoons around distant gas giants, perhaps in the Goldilocks zone of another star? We will look at how telescopes can infer hidden moons from tiny timing shifts, and how future missions could search their atmospheres for biosignatures. Optimistically speaking, if you stay to the end, we will put all of this together and ask one decisive question: which single moon, if any, is the top candidate for hosting life right now? And how soon could a spacecraft or telescope actually prove us right, or force us to start the map again from scratch? How to build a habitable moon in the first place? If we are trying to rank the best moons for life, we first have to ask a deceptively simple question: what does any world actually need to be habitable? In the hunt for alien life, this is where everything begins. Astrobiologists usually talk about three classic ingredients. First, liquid water, because it is an incredible solvent that lets molecules move, meet, and react. Second, a source of energy, something that keeps chemistry running away from equilibrium instead of freezing into stillness. And third, the right chemistry itself, carbon-based molecules, plus elements like nitrogen, phosphorus, and sulfur, all circulating in a way that life can access. Wherever those three come together for long enough, our alarm bells start ringing. For planets, we normally frame this in terms of the Goldilocks zone around a star. Too close, and starlight boils oceans into steam. Too far, and water locks into permanent ice. So, let's begin with that picture. Earth sitting at just the right distance from the Sun, with a breathable atmosphere to moderate temperatures. Mars lies near the outer edge and struggles to keep water stable. Venus is inside the inner edge and shows us what a runaway greenhouse can do. But while this star, planet dance dominates classical habitability, moons have another card to play. They can make their own heat. Instead of relying only on distance from the star, many icy moons live far beyond the traditional Goldilocks zone, yet keep internal oceans liquid through tidal heating. As they orbit a massive planet, gravity flexes and kneads their interiors, like repeatedly bending a paperclip until it gets hot. That constant flexing creates frictional heat, which can melt internal ice into deep global oceans. This means a moon tens of times farther from the Sun, then Earth can still hide a warm sea under a frozen shell. It should be noted that this splits habitability into two sets of controls. The star factors include the overall radiation environment, the distance from the Sun, and how exposed the system is to high-energy cosmic rays. Around an active red dwarf, for example, flares and particles can strip an atmosphere or sterilize a surface. The moon factors, though, are more intimate. How strong the tidal heating is, what the interior is made of, whether salts and organics are mixed into the water, and how thick the overlying ice shell becomes. And here is the twist. Some of the best habitats may sit in permanent darkness, with no sunlight at all. On Europa, or Enceladus, hydrothermal vents on the seafloor could drive chemical gradients that power entire ecosystems, just as they do at Earth's deep ocean vents, where sunlight never reaches. So it's time to find out the truth. If life can thrive in these hidden oceans, what would that mean for the countless unseen moons orbiting distant exoplanets? And which one in our own system should we investigate first? Jupiter's domain, where the first ocean worlds hide. If hidden oceans are the stage, then where is the grandest performance in our own backyard? To answer that, we have to shift our gaze from a single icy moon to an entire miniature solar system. Jupiter is not just a planet. With its enormous mass and more than 90 known moons, it behaves like a scaled-down version of a star system, complete with its own Goldilocks zone for ice and rock. 4 of those moons, Io, Europa, Ganymede, and Callisto, are so large and complex that they are worlds in their own right. In the hunt for alien life, these are not side characters, they are main targets. Why? Because Jupiter's gravity does something our sun cannot do at that distance. It grabs its moons, flexes them, and refuses to let go. As they orbit, they are constantly stretched and squeezed by Jupiter and by each other. This tidal forcing turns orbital motion into internal heat, warming their interiors even though they sit far from the sun's warmth. This means that ice that should be frozen solid for billions of years can melt deep below the surface, forming vast subsurface oceans. But while they share the same giant planet, the 4 Galilean moons form a dramatic spectrum. Io is the innermost, and it is a volcanic hellscape. Its surface is a constantly changing patchwork of lava lakes and sulfur plains, with no stable ice, no calm oceans, and almost no chance of a habitable environment. Move one step outward, and the picture changes completely. Europa looks almost serene, a smooth, bright shell of ice, crisscrossed by long, dark fractures. Beneath that shell, the data strongly suggest a global ocean, potentially containing more water than all of Earth's oceans combined. Further out, Ganymede is even larger than Mercury, and it should be noted that it has its own magnetic field. Models indicate multiple stacked ocean layers sandwiched between high-pressure ice phases. Callisto, on the edge of Jupiter's domain, is heavily cratered and ancient, a frozen relic that still may hide a buried ocean preserved beneath its battered crust. Here is the twist. These moons do not simply orbit Jupiter in silence. They are immersed in its powerful magnetic field and intense radiation belts. Charged particles sweep past them, and their buried oceans, if salty, can generate induced magnetic signatures that subtly distort Jupiter's field. By measuring those distortions, spacecraft like Galileo, and soon JUICE and Europa Clipper, can infer where the hidden water is, and how deep it lies. The same radiation that would sterilize any exposed surface life may actually help us map where life could exist underground. So, let's begin to focus. Among all of Jupiter's worlds, Europa stands out, a cracked, gleaming ice ball, likely rich in liquid water, energy, and chemistry. Optimistically speaking, it is the closest thing we have to an accessible ocean exoplanet, and very soon, we will fly a dedicated mission right through its radiation-blasted neighborhood to test whether this distant moon could truly be habitable. Europa, the classic hidden ocean that refuses to stay quiet. So what makes this smooth, bright ice ball so special that many scientists quietly rank it above Mars in the hunt for alien life? Europa looks simple from far away, but the closer we examine it, the stranger it becomes. Its surface is almost blindingly bright, a shell of water ice, reflecting sunlight like powdered glass. But that shell is not calm. It is crisscrossed by reddish-brown lines, some stretching thousands of kilometers, like a planet-sized spiderweb frozen in mid-tear. These lineae slice through older terrain, overlap, and twist, telling us the ice has been pulled, cracked, and shifted over and over again. Mixed in are regions of chaotic terrain where blocks of ice seem to have broken, rotated, and refrozen in jumbled rafts. This means the shell is mobile, not rigid, and very likely floating on something that can let it move, a global liquid ocean. But surface appearance alone is not enough, so it's time to find out the truth using hard data. When the Galileo spacecraft flew through the Jupiter system, it measured Europa's magnetic environment. As Europa orbits through Jupiter's powerful magnetic field, an electrically conductive layer inside the moon responds, creating an induced magnetic field of its own. The simplest explanation is a salty, global ocean, tens of kilometers beneath the ice. Surface geology that behaves as if the crust can decouple and slide, plus hints of water, vapor plumes seen by the Hubble Space Telescope, all point in the same direction. Europa is hiding an ocean deeper than Earth's. Where does the energy come from to keep all that water liquid so far from the sun? Tidal heating. Europa is locked in a gravitational dance with Jupiter and the other large moons, constantly flexed as it orbits. That flexing dissipates energy as heat inside the interior. At the seafloor, where hot rock meets cold water, we probably get hydrothermal vents, similar to the black smokers on Earth's mid-ocean ridges. On our own planet, such vents host thriving ecosystems that do not depend on sunlight at all, just chemistry. And chemistry is where Europa becomes even more intriguing. Jupiter's radiation bombards the surface ice, breaking molecules and creating oxidants and salts. It should be noted that these materials might be cycled downward through cracks or convection in the ice shell. If oxidants from above meet reduced compounds from hydrothermal activity below, you get chemical energy gradients that microbes could exploit even in total darkness. Europa Clipper is designed to test this entire picture. In the hunt for alien life, we finally have a dedicated scout. The spacecraft will perform dozens of close flybys, using ice-penetrating radar to estimate shell thickness, magnetometers, and gravity measurements to constrain the ocean's depth and salinity, and spectrometers to map surface chemistry in detail. It will literally sniff for plumes, flying through any detected vapor to sample water, salts, and organics directly. Optimistically speaking, it could even identify regions where fresh ocean material has recently reached the surface. So, let's begin to think of Europa not just as a frozen moon, but as an entire ocean world, with weather, tides, and seafloor volcanoes we have never seen. If Europa Clipper confirms this dynamic picture, the next logical step is bold: send a lander to touch that ice, and maybe, one day, a probe that drills or melts its way into the ocean itself. Ganymede and Callisto, giant, layered, and maybe surprisingly, wet Europa might be the poster child for ocean worlds. But what if the biggest secrets are hiding in its quieter siblings? Two of them are Ganymede and Callisto, and in the hunt for alien life, we cannot afford to ignore these giants. Ganymede, first. This moon is so large that if it orbited the Sun instead of Jupiter, we might casually call it a small planet. It is bigger than Mercury, yet made mostly of ice and rock, and it does something no other moon in the solar system does. It has its own magnetic field. This means its interior is not just a frozen block. It should be noted that a magnetic field usually hints at layers, including a conductive, salty ocean wrapped around a metallic core. Inside Ganymede, models suggest a strange sandwich of water and ice. Instead of one simple ocean, there may be multiple stacked layers: ice on top, liquid water below, then high-pressure ice, then more water, repeating downwards. These exotic ice phases only appear under enormous pressure, and they might separate much of the liquid from the rocky seafloor. Why does that matter? Because contact between water and rock is where chemistry becomes interesting, where hydrothermal vents can form, and where life's ingredients might be brewed. If most of Ganymede's ocean is insulated from rock, its habitable potential changes dramatically. So how do we know any of this and not just guess? Magnetic field measurements from the Galileo spacecraft, combined with gravity data, show that something inside both Ganymede and Callisto is conducting electricity and shifting mass in a way best explained by global subsurface oceans. But while Europa's surface is young, fractured, and clearly active, Ganymede, and especially Callisto, look ancient. They are covered in impact craters, frozen in time. So it's time to find out the truth. Can a world look dead on the outside and still hide a deep, persistent ocean within? Here the habitability trade-offs become fascinating. Ganymede's internal heating and magnetic field could drive more dynamic environments, but its oceans may sit deeper under thicker ice, harder for energy and nutrients to cycle. Callisto, by contrast, seems more geologically quiet, with an ocean that might be more isolated, yet it orbits farther from Jupiter's intense radiation belts. Optimistically speaking, that calmer radiation environment could make any near-ice chemistry or thin atmosphere slightly more welcoming for fragile organic molecules. The European Space Agency's JUICE mission is heading straight into this mystery. It will spend years in the Jovian system, then settle into orbit around Ganymede itself, mapping its gravity, probing its magnetic field, and sampling the thin atmosphere for hints of water and salts. This means we will finally test whether these deep, layered oceans are real, and how thick that ice roof truly is. And if even these heavily buried oceans turn out to be long-lived and complex, what does that say about how many hidden, habitable environments might exist on exomoons we have not even detected yet? The next moon on our list pushes that question even further. Saturn's secret, why its tiny moons punch above their weight. The next moon on our list does something bold. It leaves the ocean door not just unlocked, but wide open. When we shift our gaze from Jupiter to Saturn, it can feel at first like we are stepping down a level. Jupiter has the giant moons, the strong magnetic field, the dramatic radiation belts. Saturn, with its pastel rings and smaller satellites, looks gentler, almost delicate. But while Jupiter's system dominates in size, Saturn's moons quietly dominate in mystery. In the hunt for alien life, this is where the underdogs start punching far above their weight. It should be noted that Saturn offers one crucial advantage before we even talk about oceans or chemistry. Its radiation environment is far less brutal than Jupiter's. Around Jupiter, intense charged particles sweep through the system, stripping atmospheres and frying electronics. Any probe that dives close to Europa has to wear extreme radiation shielding, and any fragile biology near the surface would be under constant assault. Around Saturn, the magnetic field is weaker, the belts are thinner, and space is just a little less hostile. This means our instruments can survive longer, orbit closer, and sample more daringly. And, if life does exist near the surface or in plumes, it has a slightly friendlier neighborhood to try to persist in. We are still in deep space, but the rules are softened just enough to matter. Yet Saturn's moons are not cold, frozen stones. Orbital resonances and Saturn's own gravity twist and flex them as they orbit, turning tides into heat. Even objects only a few hundred kilometers across can be kneaded from the inside, keeping their interiors warm, their ice cracked, and in some cases, their oceans liquid. Tiny Enceladus, only about 500 kilometers wide, should by all rights be a dead ice ball. Instead, it behaves like a world with a heartbeat. Here is our pattern interrupt. While Jupiter's ocean worlds hide everything under thick ice and subtle magnetic clues, Saturn changes strategy. One moon, Enceladus, literally sprays its ocean into space through great plumes at its south pole. Another, Titan, calmly holds entire lakes and seas of liquid hydrocarbons right on the surface, under a thick, orange atmosphere. One world invites us to fly through an ocean's breath, the other lets us watch alien rain fall into methane seas. So, let's begin to see why that matters. Cassini flew through Enceladus's plumes many times, treating them mainly as a way to probe an icy moon's geology. Only later did the data reveal salts, water vapor, and complex organic molecules, hinting at hydrothermal vents on a hidden seafloor. Optimistically speaking, we may already have sampled material from a habitable ocean without designing the mission to search directly for life. So it's time to find out the truth, what might already be sitting in those archives, waiting for us to reanalyze the data with new questions. And what will happen when we return to fly through that alien spray on purpose? Enceladus, the moon that sprays its ocean into space. What kind of world sprays its ocean directly into space? In the hunt for alien life, there may be no place stranger or more inviting than Saturn's tiny moon Enceladus. At first glance, Enceladus should not be special. It is small, only about 500 kilometers across, bright white, and locked in a cold orbit around a distant gas giant planet. Yet when Cassini arrived at the Saturn system, this little ice-covered sphere revealed a spectacular secret. Near its south pole, long fractures slice across the surface, and from these so-called tiger stripes, geyser-like plumes erupt hundreds of kilometers into space. These plumes are not just pretty, they are powerful enough to feed Saturn's diffuse E-ring with a constant stream of fine ice particles. So while Enceladus looks frozen and still on the outside, its contribution to the ring system tells us something is active deep within. But what, and how could such a small moon generate that much material, continuously, for probably millions of years? So, let's begin with what Cassini actually did. Mission planners realized that by flying the spacecraft straight through those plumes, they could sample whatever Enceladus was throwing into space. No drill, no lander, just a high-speed taste test of an alien ocean. Instruments detected water vapor, salts similar to those in Earth's oceans, simple organics like methane, and more complex organic molecules containing carbon, hydrogen, oxygen, and nitrogen. It should be noted that Cassini also found something far more subtle and important: tiny grains of silica, just billionths of a meter across. These silica nanoparticles are the real game changer. On Earth, we see the same kind of particles form when very hot water, perhaps 90 degrees Celsius or more, circulates through rocky seafloor and then cools. This means that deep inside Enceladus, hot water is likely reacting with a rocky core before being blasted back out through those fractures. In other words, Enceladus probably has hydrothermal vents on its seafloor, not entirely unlike the black smokers on Earth where microbial life flourishes without sunlight. So it's time to find out the truth. Does this tiny moon tick the boxes for a habitable environment, even if we never see its surface melt? The checklist is surprisingly complete. A global, subsurface ocean of liquid water beneath the ice, energy from tidal flexing as Enceladus orbits Saturn, and from hydrothermal systems in its rocky interior. Organic chemistry already confirmed in the plume data, and crucially, direct access to that ocean material in space, where a spacecraft can fly through and collect samples without ever touching the ground. Optimistically speaking, that makes Enceladus one of the easiest places in the entire solar system to search for biosignatures. We do not need to land. We do not need to drill through tens of kilometers of ice. A future mission, equipped with dedicated life detection instruments, could simply dive through the plumes again and again, reading the chemistry of the spray in exquisite detail. Would we find complex, organic patterns that only biology can explain? Actual cell-like structures frozen in the ice grains? Or a sterile, but still fascinating prebiotic ocean? The stakes are high. Because if a tiny moon around a distant planet can host an active, habitable ocean, what does that imply for the countless icy moons we will never see directly around exoplanets in the Goldilocks zone of their own stars. In the next section, we will turn from Enceladus's easy-access ocean to another world where the ocean is deeper, darker, and much harder to reach, but perhaps just as promising. Titan, an alien Earth with two different ways to be habitable. If Enceladus is our accessible ocean world, Titan is something stranger. What do we do with a moon that looks like an Earth-like planet in silhouette, yet runs on a completely different liquid? So, let's begin with that first glance. When we see Titan through spacecraft cameras, it is wrapped in a thick, orange atmosphere dominated by nitrogen. Just like Earth's, there are clouds, storms, seasons, even rain and rivers that carve branching channels across the surface. But while Earth's rivers carry water, Titan's flow with liquid methane and ethane, chilled to around -180 degrees Celsius. Lakes and seas spread across the polar regions, dunes march across equatorial plains, and yet the entire system is locked in deep freeze. In the hunt for alien life, this is a profound twist. We know that stable liquids on a surface are a key ingredient for habitability. On Titan, that box is clearly ticked, but with hydrocarbons standing in for water. It should be noted that at these temperatures, chemistry moves slowly, and any water on the surface is rock-hard ice, not a solvent. This means the familiar biochemistry that works in our oceans would almost certainly fail in Titan's lakes. However, the story does not stop at the surface. Gravity measurements and Titan's slight wobble in its orbit, recorded by the Cassini mission, strongly suggest that beneath the rigid icy crust lies a global subsurface ocean. Models indicate this ocean is made of water mixed with ammonia, which lowers the freezing point and allows it to remain liquid over geologic time. In other words, under a world of frozen methane rain, there could be a dark, salty, more conventional habitat. Above that hidden ocean, Titan's atmosphere is a chemical factory. Sunlight and energetic particles from Saturn's magnetosphere break apart methane and nitrogen, then recombine them into complex hydrocarbons and nitriles. These organic molecules clump, grow, and eventually drift down like a slow, constant snow, coating dunes and filling basins. If we want to understand how prebiotic chemistry might proceed before life, Titan offers raw material on a planetary scale. So we end up with two very different possibilities. The buried water ammonia ocean might be habitable in a way we recognize from Europa or Enceladus, but it is difficult to reach. The surface lakes, by contrast, are exposed and easy to study, yet probably too cold for water-based life. Could they still host exotic chemistry, or even a truly alien form of life that uses liquid methane as a solvent? So it's time to find out the truth, and that is where Dragonfly comes in. This nuclear-powered rotorcraft will not just land once, it will fly from site to site through Titan's dense atmosphere, sampling dunes, ancient impact sites, and possibly the edges of dried lakes. By analyzing organic-rich sediments and the surrounding atmosphere, Dragonfly will test whether Titan's chemistry has taken steps toward biology, and its measurements of Titan's interior structure will indirectly constrain that hidden ocean below. Optimistically speaking, Titan could show us both how life like ours might begin in a subsurface sea, and how utterly alien life might arise in a methane world. But if Titan is a frozen laboratory for possibilities, what happens when we turn to a moon where the ocean is not buried so deeply and the radiation environment is far more extreme? The maybe moons, Mimas, Dione, and other quiet suspects. If Europa and Enceladus are the loud, obvious ocean worlds, what about the quiet ones? The moons that, on first glance, look utterly dead until the data whisper otherwise. So, let's begin with the strangest suspect of all, Mimas. For decades, it was the punchline of Saturn's system, a battered ice ball that just happened to look like the Death Star. No atmosphere, no plumes, just craters on craters. In the hunt for alien life, Mimas was filed under background scenery. But while its surface screams frozen solid, its motion tells a different story. Cassini measured a tiny wobble in Mimas's orbit and spin, a libration that is hard to explain if the moon is rigid all the way through. When scientists plugged that wobble into internal structure models, they found something shocking. This means Mimas might hide a young subsurface ocean, or at least a partially melted interior, beneath ice only a few tens of kilometers thick. Here is the pattern interrupt. The most boring moon in the picture may be an ocean world in disguise. It should be noted that the evidence is subtle. There are no dramatic geysers, no clear magnetic signature, yet a slightly different assumption about ice thickness or rock content flips the answer from warm interior back to solid ice ball. And Mimas is not alone in this limbo. Farther out, Dione and Rhea circle Saturn in quieter, wider orbits. At first they looked like generic icy moons, but Cassini's gravity measurements hinted that Dione's interior might be layered in a way consistent with a buried water ocean. There are faint fractures and old hints of past activity on its surface. Rhea, even larger, shows clues in gravity and magnetic data that could be explained by a thin internal water layer as well, although alternative models exist. So it's time to find out the truth. Are these really ocean worlds, or are we seeing ghosts in incomplete data? The challenge is that we are pushing our instruments to their limits. Tiny variations in how fast a spacecraft flies past, or how a moon slightly speeds up and slows down in its orbit, must be turned into a full 3D map of its interior. Change the assumed temperature, or the saltiness of the water, and a habitable model can vanish. Yet even marginal candidates matter. If several small moons in one planetary system can maintain, or recently develop, internal oceans, then habitable niches might be far more common than the few famous examples suggest. Optimistically speaking, a gas giant's retinue could host multiple time windows where chemistry, energy, and liquid water overlap. And if we are still adding new maybe oceans around Saturn, what are we missing around Uranus and Neptune, where we have almost no close-up data at all? What about exomoons around distant planets in the Goldilocks zone of their star, where our telescopes only see the faintest dips in light? In the hunt for alien life, the real mystery may be that the universe is hiding its best laboratories just out of reach, beyond Saturn, the forgotten ocean worlds of Uranus and Neptune. So if Jupiter and Saturn are already overflowing with hidden oceans, what happens when we look even farther out, to the ice giants? Uranus and Neptune each carry their own miniature systems of icy moons, yet we have almost no idea what is really happening on any of them. It should be noted that our entire picture of these distant worlds comes from one spacecraft, Voyager 2. Racing past in the 1980s, a few hours of flyby data for each planet, a handful of images per moon, and then silence for decades. But while the pictures are old and blurry by today's standards, there are clues in them that are hard to ignore. Neptune's largest moon, Triton, is the standout example. Instead of quietly orbiting in the planet's equatorial plane, it moves backwards in a strange, retrograde orbit. This means Triton is probably a captured Kuiper Belt object, a frozen relic from the outermost reaches of the solar system. Its surface looks young and smooth, with very few impact craters, and Voyager actually saw dark plumes rising from the surface, likely nitrogen geysers or cryovolcanoes. In the hunt for alien life, that combination is electrifying. A captured icy body, active geology, and a surface made of nitrogen and water ice all point toward internal heat and, quite possibly, a buried ocean. Many models suggest that under Triton's crust, a salty, ammonia-rich sea could still be liquid today, insulated by thick ice and heated from within. If so, Triton might be one of the most promising ocean worlds in the entire Neptune system, and we have only skimmed past it once. Uranus tells a similar, haunting story. Moons like Miranda and Ariel look nothing like dead, frozen rocks. Miranda is carved up by enormous canyons and patchwork terrains, as if the moon was shattered and reassembled. Ariel shows signs of resurfacing and long tectonic fractures. Where does that kind of energy come from, in a place so far from the sun? Optimistically speaking, internal heating and perhaps long-lived liquid layers beneath the ice are very much on the table. The problem is that we lack the detailed magnetic and gravity data that revealed oceans at Europa, Ganymede, and Enceladus. We have no precise measurements of how these moons flex in their orbit, no close surveys of their thin atmospheres, if they even have any. So it's time to find out the truth, but we are still waiting for the missions that can actually go there. Theoretical work, however, refuses to wait. When scientists model medium-sized icy moons throughout the outer solar system, they find that many should be able to maintain internal water for billions of years, as long as there is enough rock, enough salt, and some tidal or radioactive heating. This means that even with our limited exploration, the count of moons that could hide life supporting oceans already stretches into the dozens. So, let's begin to think bigger. If our own backyard beyond the frost line is packed with possible ocean worlds we have barely seen, what might be waiting around distant gas giants in the Goldilocks zone of their star, where we cannot even see the moons directly yet? Reframing the question, what counts as habitable now? We have to pause and ask a harder question. If almost every major icy moon we look at seems to hide an ocean, how do we avoid calling the whole outer system habitable and walking away satisfied? So far, our journey has taken us past a surprising crowd of candidates. At Jupiter, Europa almost certainly holds more water than all of Earth's oceans. Ganymede may stack multiple oceans in layers, and even Callisto refuses to rule itself out. At Saturn, Enceladus is venting a global sea directly into space. Titan couples a likely internal water ocean with surface lakes of liquid hydrocarbons, and Mimas has quietly joined the maybe list. And it should be noted that beyond them, Uranus and Neptune probably host their own hidden ocean moons we have barely resolved as dots. In the hunt for alien life, that sounds like an embarrassment of riches. But while could there be water? Was once the main question, it is no longer enough. The refined question now is this: which moons offer conditions stable and rich enough for life to emerge, persist, and perhaps even evolve complexity? Not just any ocean, but the right kind of ocean, in the right kind of environment, for a very long time. To make sense of this, we need a simple way to compare worlds that could not be more different from an Earth-like planet. So, let's begin with 4 big pillars. First, water. Not only whether liquid water exists, but how much of it is actually available for chemistry, rather than locked away in high-pressure ice. Second, energy, tidal heating, radioactive decay, and seafloor hydrothermal vents, and how intense and sustained those power sources are. Third, chemistry. Are there organics, salts, and strong redox gradients to drive metabolism, like the ones Cassini hinted at inside Enceladus? And fourth, time and stability. Has the ocean been there for hundreds of millions or billions of years, or is it a brief, dramatic phase? Here is the tension. Enceladus is small, geologically active, and spectacularly generous. We can literally fly through its plumes and sample an alien ocean without drilling a meter of ice. This means it is an almost perfect laboratory for testing whether ocean chemistry can cross the line into biology. But a moon this tiny may cool and freeze on relatively short cosmic timescales. Ganymede and Titan, by contrast, might host vast, long-lived oceans, buffered by thick shells of ice, and in Titan's case, a dense atmosphere that shapes weather and climate. They could be incredibly stable habitats, yet they are also more sealed off, harder to probe directly, and their most interesting layers may be buried far below what any lander can easily reach. Pattern interrupt. What if our best target is not the easiest to sample, or the most dramatic on camera, but the one that quietly checks all 4 boxes the most consistently? So it's time to find out the truth. In the next part of this episode, we will start using this framework to rank and contrast our top ocean moon candidates, and then push the same logic outward to hypothetical exomoons orbiting distant gas giants in the Goldilocks zone of their star, where our only clues will come from the faintest possible data, the fine print, how little we still know about these oceans. But before we start handing out gold medals to our favorite ocean moons, we need to be honest about something. How much of this picture is solid fact, and how much is an educated sketch filled in between the lines of very limited data? In the hunt for alien life, it should be noted that almost everything we think we know about these hidden oceans is indirect. We do not see Europa's waves or Enceladus's seafloor. Instead, we watch how a moon's gravity field tugs on a spacecraft, how its magnetic environment wiggles as it orbits a giant planet, how cracked and chaotic its surface ice looks, or what chemicals show up in a passing plume. Then we feed all of that into models that have built-in assumptions about rock, water, and ice. This means every confident diagram you have seen of an icy moon sliced open, with a neat blue ocean layer and a rocky core, is really a best guess. We do not yet know the exact depths of these oceans. Are they 10 kilometers thick or 100? We do not know their salinity, their pH, or how much antifreeze chemistry, like ammonia, is mixed in. Even the temperature at the sea floor is uncertain, and that temperature controls whether hydrothermal vents, like those that may power ecosystems on Earth's deep ocean floor, can exist at all. And then, there is the most important question of contact. Is there sustained, long-term interaction between liquid water and rock, or are some of these oceans trapped between layers of high-pressure ice cut off from the minerals that would feed metabolism? Europa and Enceladus look promising, but even there, we are still inferring contact from indirect signatures of salts and silica grains. On top of that, time plays a quiet but crucial role. These moons do not live in a single state forever. Over hundreds of millions of years, tidal heating can wax and wane, orbits can shift, and interiors can freeze, partially melt, then refreeze. A moon that seems perfectly habitable to us today may have spent most of its history locked under solid ice. Another that looks frozen and dead now might once have hosted a vast, warm ocean, rich in chemistry, when the rest of the system was young. So, let's begin to think in decades, not just in snapshots. Europa Clipper and JUICE will not even arrive at Jupiter until the 2030s. Dragonfly will take years to reach Titan, and then slowly explore its dunes and possible impact melted pools. Their data will trickle back over a long time, and our ranking of which moons are truly the best bets for life will almost certainly shift with every new flyby and every new spectrum. Optimistically speaking, this uncertainty is not a weakness, it is the engine of frontier science. We are building hypotheses right now that these missions are explicitly designed to test, so it's time to find out the truth. When the first close-up results finally arrive, will they quietly confirm our favorite ocean worlds, or force us to move our hopes to a very different and much stranger? Moon. Ranking the ocean worlds. Who tops the list right now? So, if our favorite ocean worlds might rise or fall as new data arrives, where do they stand right now? In the hunt for alien life, which moon actually sits at the top of the habitability leaderboard today? It should be noted that this is a snapshot, not a final verdict, but based on what we know, Enceladus usually edges into first place, with Europa almost tied, Titan close behind as the wild card, and then Ganymede, Callisto, and Triton as powerful but more distant contenders. This means our best bets are not the biggest moons, but the ones that are the most talkative. Why does Enceladus often win? Because it is the only ocean world where we have literally flown through the spray of its interior ocean. Cassini sampled plumes rich in water vapor, salts, and organic molecules erupting from the South Pole. The chemistry points to hydrothermal vents at the seafloor, where hot rock meets cold water, exactly the kind of environment where life thrives in Earth's deep ocean. On top of that, the ice shell seems relatively thin, so a single well-designed mission could fly through those plumes again and ask a direct question: are there complex organic patterns, maybe even biosignatures, hiding in that mist? Europa, though, is right there with it. This moon probably holds more water than all of Earth's oceans combined, all locked beneath an ice crust flexed and heated by Jupiter's gravity. Strong tidal heating, a likely rocky seafloor, and hints of oxidants delivered from the surface make it a textbook habitable ocean. But while Europa may be the ultimate water reservoir, it is also harder to access. The ice is thicker, the radiation from Jupiter is brutal, and any plumes may be rarer or weaker than Enceladus's. That is why Europa Clipper is a flagship mission. We need repeated close passes just to piece together what this vast hidden ocean is actually like. Then we have Titan, and here the ranking becomes strange. On the surface, Titan is a world of liquid methane and ethane lakes under a thick orange atmosphere. Deep inside, though, there is almost certainly a water ocean. The organic chemistry up top is unparalleled, but how easily does that chemistry mix with the buried ocean where liquid water exists? Dragonfly will land on Titan and explore the surface in detail, yet even then, the connection between atmosphere, crust, and ocean might remain the big unknown. Optimistically speaking, the so-called lower-ranked worlds, Ganymede, Callisto, and Triton, are not consolation prizes. Each one offers a different blend of size, energy, and chemistry. Together, they will tell us whether habitability is rare and fragile, or something that appears again and again wherever ice and energy quietly orbit a distant planet. So, let's begin to ask a sharper question. If moons can be habitable this often in one small system, what does that imply for the rest of the universe? From moons we can visit to moons we can only infer, if habitable moons are this common right here, what about all the planets we will never visit in the hunt for alien life? This is where the story suddenly stretches from our backyard to the rest of the observable universe. Inside the solar system, we are spoiled. We can send orbiters to Europa, fly through Enceladus's plumes, even drop a rotorcraft on Titan. We get close-up images, direct samples, and precise gravity maps. But while we can do that for moons around our own star, the moons of distant exoplanets are far beyond anything we can photograph directly. Even their planets are often just a single pixel. This means that if we want to find exomoons, we have to become detectives. So how do you find a moon you cannot see? Astronomers turn to timing and shadows. When a planet passes in front of its star, the star's light dips in a very regular pattern. Add a moon, and that regularity breaks. The planet and moon both orbit a shared center of mass, so the planet arrives a little early, then a little late. These tiny schedule changes are called transit timing variations, and they can be just a few seconds. Yet, with enough data, that wobble in time can hint at a hidden companion. The second clue is the shape of the transit itself. A lonely planet produces a smooth, symmetric dip in brightness, but if a moon trails behind or leads in front, you can get an extra, shallower dip before or after the main one, or a subtle asymmetry in the light curve. It should be noted that these signals are right at the edge of what our current telescopes can reliably see, which is why every claimed exomoon so far has been controversial. JWST, Hubble, and large ground-based observatories are now pushing these methods to their limits. They are placing upper bounds on how large a moon could be around some known exoplanets, especially giant planets close to the Goldilocks zone of their star. A few candidates, like a proposed Neptune-sized moon around the planet Kepler 1625b have made headlines, but none are universally accepted yet. Optimistically speaking, we are in the messy, exciting phase where the first confirmed detection could appear in any new data release. Why does this matter so much for habitability? Because a single gas giant in the habitable zone could host an entire family of large moons, each with its own ocean, tides, and atmosphere. Instead of one Earth-like world, you could have a miniature archipelago of habitable surfaces in a single system. Tidal heating could keep water liquid even where starlight is weak, just as it does for Europa and Enceladus. So it's time to find out the truth. If we cannot see those moons directly, what kinds of chemical and atmospheric fingerprints around their planets might still betray their presence, and maybe, just maybe, the presence of life in their hidden oceans. How to spot a living exomoon without seeing it? If we cannot see an exomoon directly, how could we ever know that it is alive? In the hunt for alien life, this is one of the strangest challenges we face, detecting a living world that hides in the glare of a bigger neighbor. So, let's begin with the gas giant itself. A massive planet deep in a star's Goldilocks zone should have a certain type of atmosphere, dominated by hydrogen, helium, maybe some methane and water vapor. But place a large, volcanic, ocean-bearing moon in orbit around it, and the whole environment changes. Just as Io and Europa feed material into Jupiter's magnetic field, a big exomoon could leak oxygen, sulfur, or water vapor into space, subtly reshaping the planet's auroras and radiation belts in ways we can see from light years away. This means telescopes like DREST do not only see the planet, they see the whole system. If a moon has an atmosphere rich in oxygen, some of that gas can escape, forming a thin cloud around the planet, moon pair. Mix in methane from biology at the surface or in an ocean, and you get what astronomers call a borrowed biosignature, a combined chemical signal that does not fit a gas giant on its own. A Jupiter-like planet with a suspicious blend of oxygen and methane around it would immediately raise eyebrows. It should be noted that timing is another powerful clue. Missions like Plato will watch thousands of stars for years, recording the dips in brightness as planets transit. If a planet's transit shifts slightly forward or backward in time in a repeating pattern, or its silhouette changes shape in a consistent way, that is exactly what we expect from a moon tugging on it. Now imagine those anomalies appearing in a system that sits comfortably in the habitable zone. Suddenly, a habitable, perhaps even Earth-like exomoon becomes a serious candidate. Looking further ahead, future direct imaging observatories could go one step beyond. With giant mirrors and precise star shades, they may separate the light of a bright gas giant from the pinpricks of one or more moons. Then we could take spectra of the moon's reflected starlight itself, searching directly for oxygen, methane, carbon dioxide, maybe even seasonal changes that hint at active biology. Optimistically speaking, this would turn distant moons into fully characterizable worlds. But what happens if we see the chemistry first and the moon later? If GWS or a successor detects a gas giant with a stable, repeating mix of gases that screams biology yet makes no sense for the planet, we might be forced into a bold conclusion: an unseen exomoon is alive, changing the atmosphere of its giant host from the shadows. And if that happens, the next question becomes unavoidable. How do we go from a ghostly chemical whisper to a detailed portrait of that hidden world? Europa Clipper, JUICE, Dragonfly are just moments for moons to answer that. We do something very different from staring at faint dips of light around a distant star. We go there. For moons in our own system, the equivalent of a James Webb verdict is not a spectrum from 40 light-years away, but a spacecraft diving through the radiation belts of Jupiter or settling into the orange haze of Titan. In the hunt for alien life, 3 missions stand out as our just moments for moons: Europa Clipper, JUICE, and Dragonfly. So, let's begin with Europa Clipper. This NASA mission will orbit Jupiter and repeatedly swoop past Europa, a world with an ocean that may hold more water than all of Earth's combined. Its main job? Turn Europa from a beautiful hypothesis into a constrained, testable system. Ice-penetrating radar will map the thickness of the ice shell and the depth and structure of the ocean below. Magnetometers will read how Europa's ocean distorts Jupiter's magnetic field, telling us about its saltiness and, indirectly, its potential to carry energy for life. Mass spectrometers will taste any plumes or tenuous atmosphere they can find, hunting for salts, organics, maybe even complex molecules that should not be there by accident. High-resolution cameras will tie all of this to the surface, cracks, ridges, chaos terrain that might mark places where the ocean is punched through. This means we finally get to test whether Europa's ocean is just liquid or truly habitable. But while Europa Clipper dissects one moon in detail, ESA's JUICE mission takes a broader broader view of the Jovian system. Juice will orbit Ganymede, the only moon with its own magnetic field, and fly by Europa and Callisto along the way. Again, the pattern is familiar from JUST: multiple targets, one toolkit, consistent comparisons. Radar and gravity measurements will probe layered oceans inside Ganymede and possibly Callisto. Cameras and spectrometers will map ice, salts, and organics on their surfaces, linking geology to interior oceans and tidal heating. Pattern interrupt: none of these missions actually lands. For that, we leave Jupiter and head to Saturn. Dragonfly is a nuclear-powered rotorcraft that will fly through Titan's thick atmosphere and land again and again on its surface. Titan is not Earth-like in temperature, but it is strangely Earth-like in complexity, with rivers, dunes, and lakes. Dragonfly's mass spectrometers and cameras will analyze organic rich sands and ices, testing how far prebiotic chemistry can progress in a cold, hydrocarbon world that might also hide a deep internal ocean. It should be noted that, just as GAWS has ruled out certain atmospheres for TRAPPIST-1 planets, these missions will rule out or confirm specific ocean depths, energy sources, and chemical environments. Optimistically speaking, by the 2030s and 2040s, once Europa Clipper and JUICE have built up their datasets and Dragonfly has hopped across Titan for years, we will have something like a statistical picture of which types of moons are truly habitable, and somewhere in that flood of data, there could be a single spectrum, a strange plume, or an unexpected chemical ratio that quietly says, this ocean is not just habitable, it is inhabited, so it's time to find out the truth about what it would take to recognize that signal with confidence. If life exists in a dark ocean, what would it be like? If that ocean really is inhabited, what is it like to be alive in a world with no sunrise? On Earth, we already have a clue. There are places on our own planet where sunlight never reaches, where the surface world might as well not exist. Around deep-sea hydrothermal vents, thousands of meters down, entire ecosystems bloom in permanent night. Giant tube worms, blind shrimp, strange white crabs, and dense bacterial mats all thrive there, powered not by our star, but by chemistry. These communities live on chemical energy from the vent fluids, rich in hydrogen, methane, and sulfides. Microbes use those redox reactions the way plants use photons, building organic matter in the dark. It should be noted that this is not a fringe curiosity. These ecosystems are productive, structured, and surprisingly complex, despite being cut off from sunlight. In the hunt for alien life, that is a crucial proof of concept. Now take that idea and scale it up to an entire ocean under ice. On Europa or Enceladus, tidal heating could drive hydrothermal vents on a rocky seafloor. Oxidants made in the surface ice by radiation from the parent planet might slowly drift downward, meeting reduced compounds from the core. Where those two streams of chemistry collide, chemolitho-autotrophic life could exploit the redox gradient, just as vent microbes do here. So, let's begin to imagine what that life might look like. At the base, there would almost certainly be microbes, cells clinging to mineral chimneys, drifting in the water column, forming biofilms on rock and ice. Some might use hydrogen and carbon dioxide, others sulfur or iron. This means a whole invisible forest of chemistry, building the organic scaffolding for everything above it. But could there be more than microbes? Could a dark, sealed ocean support multicellular creatures, large bodies, even something that thinks? On Earth, vent ecosystems host tube worms longer than a person, clams the size of dinner plates, and complex food webs, so complexity is not forbidden by darkness. The real constraint is energy flux. Without a star bathing the surface, the total power available is lower, and that limits how big and how fast evolving an ecosystem can be. Nutrient recycling would also be slower, dead material might sink and accumulate on the seafloor, locking away resources unless specialized decomposers evolve. And in a global ice-capped ocean, there is no easy way to manipulate an external environment. No fire, no tools, no sky to observe. Optimistically speaking, intelligence could still emerge as intricate social behavior, communication, or navigation using magnetic fields, but civilization in the Earth-like sense may be very unlikely. Yet, we should be careful not to underestimate evolution. Even with tight energy budgets, life might discover bizarre strategies, organisms that farm vent microbes, creatures that migrate with tidal currents, or slow, long-lived predators that sense heat and chemistry instead of light. So, if we pierce one of these ice shells and find only microbes, does that make the discovery less profound, or more so, because it proves the universe can spark life in places we once thought utterly sterile, redefining the habitable zone, planets, moons, and everything between? And if life can bloom in those dark oceans, where does that leave our old idea of the so-called Goldilocks zone? For decades, we drew a neat ring around a star and said, here is where a planet with an Earth-like atmosphere can keep liquid water on its surface. Too close, and it boils away. Too far, and it freezes. Simple, elegant, and, as we are now realizing, far too narrow. Ocean moons break this tidy picture. Europa or Enceladus are far outside the Sun's classical habitable zone, yet everything about their data screams potentially habitable environment. They use Jupiter and Saturn as gravitational engines, flexing their interiors and turning orbital stress into heat. This means liquid water can exist, not because the star shines just right, but because the moon is kneaded like dough by the planet it orbits. In the hunt for alien life, that is a profound shift. Habitability is no longer just about distance from a star, it is about energy and chemistry, wherever they arise. Starlight works, but so do tidal forces, radioactive decay in a rocky core, and perhaps even slow chemical reactions between rock and water at the seafloor. A frozen surface can hide an ocean richer in energy than some bare rock inside the traditional Goldilocks zone. It should be noted that this radically changes the numbers. If we only count Earth-like planets in the right orbit, our galaxy looks moderately generous. But while a single Earth analog gives you one obvious habitat, a single giant planet could host several large moons, each with its own internal ocean. Imagine every Jupiter-like world and every star system multiplying its habitable real estate, Europa-style oceans, Titan-style chemistry, Enceladus-style vents, all in parallel. Optimistically speaking, the census of possible homes for life might jump by an order of magnitude, maybe more. And that is before we consider truly free-floating planets and moons drifting through deep space, far from any star, yet still warm inside from tidal relics or radioactive heat. A world like that would look utterly dead from the outside, a black marble in the dark, while inside it might host more liquid water than Earth. So it's time to find out the truth. We are living at the exact moment when this expanded view of habitability is being tested. Europa Clipper, JUICE, Dragonfly, and telescopes like Jubilist are not just checking boxes, they are asking whether our new, generous definition of habitable actually matches reality. Will they reveal that ocean moons are common abodes of life, quietly filling the universe with biology we have never seen before? Or will they show that even in these perfect-seeming habitats, something crucial is missing, and that Earth is far more unusual than all these worlds suggest? The answer may depend on one specific kind of signal, and whether we are clever enough to recognize it when it finally appears. Every moon that could hide life, what we've learned tonight. So what have these worlds actually told us tonight? They look distant and exotic, but together they sketch a single, radical idea about where life can exist in the universe. Europa was our first clue, a world the size of our moon, yet hiding an ocean with more water than Earth beneath a cracked, glowing shell of ice. Tidal forces from Jupiter knead it like dough, driving possible hydrothermal vents on the seafloor in the hunt for alien life that is about as close to an Earth-like deep ocean as we have found so far. Then, Enceladus raised the stakes. This tiny moon of Saturn sprays its secrets directly into space. We have flown through its plumes and tasted salty water, organics, and heat-driven chemistry from a global sea in permanent darkness. If life can emerge anywhere without sunlight, this is where many scientists would place their bets. Titan showed us a different path. Lakes and seas of liquid hydrocarbons under a thick orange atmosphere, and beneath that, a buried water, ammonia ocean. Two stacked oceans in one frozen shell. It should be noted that this moon alone proves that habitable chemistry does not have to look like Earth's surface at all. Ganymede and Callisto offered scale. Ganymede, with its own magnetic field, likely holds layered oceans sandwiched between high-pressure ice, while Callisto may cradle a briny sea just under its battered crust. Quiet, heavily cratered, yet potentially hiding more liquid water than any rocky planet in the system. Triton pulled us outward to a captured world with geysers and a probably young, active interior. Its strange orbit and dark surface suggest a past as a dwarf planet, but while its history is messy, its message is clear. Even far from the sun, internal energy can keep a world alive inside. And then the maybe moons, from Mimas with its suspicious wobble to distant candidates we have only glimpsed in sparse data. They whisper that hidden oceans might not be rare special cases, but a default outcome when ice, rock, and tidal heating meet. This means our solar system alone could host a whole family of stable, shielded oceans, each one protected from radiation and surface disasters, quietly running chemistry for billions of years. Optimistically speaking, if that is true here, then in the galaxy there could be billions of such ocean worlds, especially once we add exomoons we have not yet resolved. Pattern interrupt. What if the first aliens we meet are not on a planet at all? They might be microbes drifting in black water under kilometers of ice, never seeing their star, yet built from the same atoms and physics that eventually produced us. So it's time to find out the truth. We live at a unique moment. We have identified the suspects, we are building the probes and telescopes, and the missions are leaving Earth. The remaining question is simple, but uncomfortable. How much do we actually care about getting the answer? And what are we willing to do next to hear whatever those oceans have to say? Your role in the search beneath the ice, that answer, is not just up to scientists in clean rooms. It's partly up to us. Imagine the moment. A mission team steps up to a podium, the room is silent, and the headline ripples across the world. Strong evidence for life in a subsurface ocean on Europa, or Enceladus, or Titan. In the hunt for alien life, that would be the day everything changes. This means every question we have asked, every late-night debate about whether we are alone, suddenly has data behind it. But while that future press conference feels distant, the path to it is being laid right now, by curiosity, attention, and public support. Missions like Europa Clipper do not appear out of nowhere. They survive decades of planning because people keep caring. When Dragonfly descends through Titan's orange atmosphere, or when we sift through J-West and Plato light curves, looking for the subtle tug of an exomoon, the world will only be watching if we choose to stay engaged. So, let's begin with something simple. If you want to follow this story as it unfolds, stay with us. Subscribe so when the first Europa Clipper images of fractured ice arrive, we can explore them together. Turn on notifications so when Dragonfly lands and starts listening for the chemistry of a strange cold ocean world, you are there on day one. When a suspicious dip in starlight hints at an exomoon in the Goldilocks zone of a distant star system, we will dive into the atmosphere models and the raw light curve data here. Beyond this channel, your role can be very concrete. It should be noted that space agencies pay attention to public interest, follow mission updates from NASA and ESA, share the discoveries that excite you, and let decision makers know that planetary exploration matters. Participate in citizen science projects that search for exoplanets and possible exomoons hidden in telescope archives. Optimistically speaking, the first hint of a habitable moon could be spotted by someone sitting at a laptop, not in a control room. Because whether the first confirmed aliens we meet are microbes under Europa's ice, strange chemistry in Enceladus's plumes, methane-based life in Titan's lakes, or something on an exomoon we have not even discovered yet, the deeper truth is the same. We have reached a point where a small species on one sunlit planet can ask these questions seriously, build the tools to answer them, and accept whatever the universe tells us. So it's time to find out the truth. Where would you place your bet? Europa, Enceladus, Titan, some hidden ocean in another system, or an exomoon we have yet to see at all? Pause for a moment, decide, then tell us in the comments, and let's keep the search and the conversation alive long after this video ends.